Okay, so it is about time to get started. So welcome back everyone to MAT1841. This is the end of the first week, I guess, since it's Thursday, Friday, Wednesday, which is how I'm sort of counting things. But yeah, and today we're going to be getting to the payoff of basically the first week's worth of material, which is we're going to be talking about Johnson-Lindenstrauss, the Johnson-Lindenstrauss Lemma, and the Gaussian Annulus Theorem, which we're going to use to prove it. So if you recall, last time we figured out that hyperballs are really, really weird in all sorts of crazy ways. And another thing we realized is that Gaussians, because they have multidimensional Gaussians, have a nice probability density function, which means that they're spherically symmetric. And so they're a useful way to sample from hyperspheres. And some of these ideas, and we're going to talk about random projections in today's lecture. So let's get started. So first, let's recall that we have, let me do this in red. Recall most points in B sub d, a ball of dimension d, are concentrated near the surface. Concentrated near the surface. And the way we drew this is we just have, well, if we draw it in 2D, we have some sphere, and then we have an annulus of width 1 over d. So this region here, and this width, so this is annulus of width 1 over d. And we proved that half of the mass of a hyperball is contained in that annulus. So now the question here is, can we say something similar about spherical Gaussians? So first we need, of course, define a spherical Gaussian. So let's just be very clear in what we're talking about. So we're going to let x be equal to a random variable, which is a d-dimensional vector. And each of our xi's is going to be a normal random variable with mean 0 and variance 1, IID. So if that's the case, then we call x vector a spherical Gaussian random variable. Spherical Gaussian random variable centered at the origin. Centered at the origin with unit variance in every direction. With unit variance in every direction. Okay, now there are a couple of things we should say about these Gaussians first. The first thing to note is that unlike hyperballs, Gaussians don't really have boundaries. So Gaussians, because the probability just like decays off as you go towards infinity. So they don't really have a boundary. The same way that a ball does. But we can still talk about the probability distribution disappearing, like where most of the probability mass is concentrated. So note that the expectation of the norm of x squared is equal to, of course, just the sum of all the different expectations squared, which is equal to d times the expectation of just x1 squared, since they all have the same distribution, which is, of course, we know that the expectation of each of these variables is 0. So this is the expectation of x1 squared minus the expectation of x1 squared. And of course, this is the normal variance formula. This is true because that's equal to 0. And this is the normal variance formula. So this is variance of x1. So this entire thing is just equal to d. And so what we're basically saying is that the expected point in a spherical Gaussian has norm squared approximately equal to d. And so we're going to call this root d the radius of the Gaussian. So unlike a radius of a ball, it's not like the boundary at which it ends, but instead this is just the expected distance away from the origin that a point is. Okay, so we know that the expected distance from the origin is square root of d, root d. And what we're now going to show is that, well, what have we been doing? We've been doing for the last couple of days. We've been saying, oh, well, we can compute these expectations, and if we compute these expectations, often if these random variables are the sum of a bunch of other random variables, then the typical example of a point is close to the expectation. So this is what we were doing with all these tail bounds and these concentration inequalities, because we were basically saying the probability that you're too far away from the expectation is small. And we can do the same thing for these Gaussians. We can say something to that effect, that most of the probability mass is concentrated near the expected value. And that's exactly what we're going to do now. So let's see. We're going to show with high probability, we are near the expectation. Let's see, Gaussian Annulus Theorem. So let's act, oh, sorry, I normally do theorems in green, I think. What's the color I've been using? Sure. So the Gaussian Annulus Theorem, which we are actually already stated on day one. So this is one of the various concentration inequalities we stated. We're actually going to prove it now, based off of the master tail bounds inequality theorem that we gave but didn't prove in day one. So again, we're going to have the same setup. We're going to let X be a vector of random Gaussians. IID. And we're going to define R to be the, well, norm of X, okay? So this is how far away you are from the origin. And this is going to be a variable that we care a lot about. And so then, if that's the case, then for any beta less than or equal to root d, the probability that the R minus root d is greater than or equal to beta is less than or equal to 3e to the minus c beta squared. So basically, all of the probability mass is concentrated near the radius. And let's prove this. So the proof is just, well, if we have that R minus root d is greater than or equal to beta, then we know that R squared minus d is greater than or equal to beta times R plus root d, which is greater than or equal to beta times root d. What are we doing there? We're just multiplying both sides by R plus root d. So that's how we get this inequality. And of course, since that means that if your this event is less likely, probability that R minus root d is greater than or equal to beta, this event's less likely than this event. The probability that R squared minus d is greater than or equal to beta times root d. And so if we're trying to bound, one of the events, you can just bound the other one because of this inequality. So now that we've done this, let me write that down just so we're all on the same page. This event is less likely because it implies the other event. Because it implies the other event. Okay, so now we can just play with this event instead. R squared minus d, well, that's just equal to x1 squared plus x2 squared plus x3 squared all the way through xd squared minus d. And you note that you have one copy of, well, you have d copies of minus 1, and you have d copies of each of these xi squareds. So we can rewrite this as x1 squared minus 1 plus dot 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 plus xd squared minus 1. And notice that we're basically breaking apart this Gaussian into all its individual Gaussians, into each of its individual Gaussians, and using something about the variance of each of those. And now what we're going to do is that we're going to define a new variable, yi, it's going to be xi squared minus 1. So let's note that the expectation of yi is equal to the expectation of xi squared minus 1, which is equal to 0. So now we have a zero-centered, a mean zero random variable, and we can actually explicitly compute each of its other moments. So let's do that, because this will become useful when we are using the master tail bounds inequality later. So let's compute the moments of this random variable. So what are the moments of this thing? We have expectation of yi. I'm going to use s because that's the power that we used in the other theorem. So the expectation of the S moment of yi is going to be less than or equal to the expectation of yi, the absolute value of y to the s, because you're just taking an absolute value. And we can also conclude that this is less than or equal to the expectation of 1 plus xi to the 2s. This logic takes 2 steps. So first, note that if xi, the absolute value of xi is less than or equal to 1, then, well, yi to the s is also less than or equal to 1, because y is xi squared minus 1. And so if the absolute value of y is less than 1, any power of it is also going to be less than or equal to 1. And furthermore, we also know that if xi is greater than 1, greater than or equal to 1, then we have yi to the s is less than or equal to xi squared to the s, which is equal to xi to the 2s. Okay, so it is just a simple case analysis, and we get that the expectation of the s moment is less than or equal to the expectation of 1 plus x to the 2s. And moving on from there, we have that is equal to just 1 plus the expectation of xi to the 2s. But of course, this is just the even moments of the Gaussian. Even moments of the Gaussian, which we can look up. Or we can compute it, but we're not going to compute it. There are just tables of these things, which we can look up. And so when we do look that up, that's just equal to 1 plus 2s minus 1 double factorial. If you guys haven't seen this notation, the double factorial does not mean you take the factorial twice. That is not what it means. It means that you're taking the product of all integers from 1 to 2s minus 1 to 2s minus 1 that have the same parity. So we get things like 5 double factorial is equal to 5 times 3 times 1 is equal to 15, or 7 double factorial is equal to 7 times 5 times 3 is equal to 105. Okay, but this is something you can look up, and it is fairly easy to convince yourself that this means that this entire thing is less than or equal to 2 to the s times s normal factorial. And so this gives us some nice bounds. So for example, we know that the variance of yi is equal to the expectation of yi squared minus the expectation of yi squared, which is going to be less than or equal to, this thing here is just 0 again. So this is going to be less than or equal to 2 squared times 2, which is equal to 8. Now we're going to recall our master Taylor-Bounds theorem, which, so let's recall it, and we're just going to plug stuff in. So this is the master Taylor-Bounds theorem. And let me write that all out again. So if we have x is a sum of a bunch of random variables, x1 through xn, where each of these is 0-centered, so xi's have 0 mean, and bounded variance, and variance at most sigma squared, then with a bunch of other technical conditions. So we're going to let choose an a such that it's greater than or equal to 0 and less than or equal to the square root of n sigma. If we have expectation of xi to the s is less than or equal to sigma to squared s factorial for all these s's equal to 3, 4, all the way to the floor of a squared over 4 pi sigma squared. Well, then we know that the probability that the norm of x is greater than or equal to a is less than or equal to 3e to the minus a squared over 12n sigma squared. Okay, so that's just a theorem that we mentioned last time. We gave a proof sketch, we didn't actually prove it. So now, unfortunately, can anyone see any problem with applying this theorem? Are there any conditions that we're not satisfying? So let's take it step by step. So do you all, so you need to change the variable names, of course, since now we're looking at these yi's. So are the yi's zero-centered? Yeah, and we have some bound on sigma squared, right? So what is sigma squared? What would we use for that? Yeah, so just 8, because the sigma squared is the variance. So variance at most 8. Well, then what we need is that we need the expectation of each of the moments of this thing to be less than or equal to sigma squared s factorial. Is that condition satisfied? Sigma squared was 8, right? Yeah, exactly. So this condition is actually not satisfied, because so this doesn't quite work. Doesn't quite work. Doesn't work because we have that the expectation of so the s moment is less than or equal to 2 to the s s factorial, but that is not less than or equal to 8 s factorial for all s greater than 3. So this doesn't work. What can we do? So one thing you could do is you could change the bounds to be larger. So you could like say, well, your variance is at most 8, but maybe your variance is at most some bigger number. But you notice that here we have this 2 to the s term. So even for any fixed big number you choose, that's not quite going to work. Yes, that's exactly right. So what you can do is you can change your random variable. So instead of looking at yi, we're going to use a different random variable. We're going to let wi be equal to yi over 2. Exactly. And so what that's going to do is then we're going to have the variance of wi is going to be less than or equal to 2. And we have that the expectation of all the s moments of wi are going to be less than or equal to 2s factorial. So then things work. So after you've done this, we just apply the master tailbound theorem with a is equal to beta root d over 2, sigma squared is equal to 2, and n is equal to d. Since we have to match up all the variable names, that's going to imply that the probability that the distance between r and root d is equal to beta, the probability that happens is less than or equal to the probability that w1 plus dot 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 plus wd, that's greater than or equal to beta root d over 2, which is less than or equal to 3e to the minus beta squared d over 48 times d times 2, which is just equal to 3e to the minus beta squared over 96. And so here, let's prove the theorem, because what we needed is we just needed some constant c. So the constant c ends up being 1 over 96. Note that this is not tight. So this is not tight, but it's good enough. So if you do a much more careful analysis, you actually have a better constant. Well, it's already exponential, so we don't actually care that much about getting a slightly better constant here. But if you're doing this in practice, you might care about like really tightening those bounds. Okay, so let's take a step back. What have we shown, and what are we trying to show, and what have we shown? Like, how does this work intuitively? What we've done is we've basically shown that all the probability mass is somehow concentrated near this radius of this Gaussian. But why is that the case? Remember, last time we did actually give the explicit probability density function of a spherical Gaussian, right? And it was it had some exponential that was determined entirely by the distance. And it decreased, it becomes less dense with the distance, right? So how is it that all the probability mass is concentrated away from the origin if the probability density function like decays as you get further away from the origin? Exactly. So because there are more points. And so this is where the in our analysis for the unit ball comes, the unit hyperball comes into play. So remember that as d goes to infinity, the amount of mass the number of points that's near the origin, that's in the unit hyperball, goes to 0. the amount of mass that's in any in that hyperball goes to 0. And so even though the probability density function is higher near the origin, there just aren't enough points that you're integrating over. And so you have to go out to a certain radius before you end up integrating enough of a probability mass. So that's the sort of intuition behind why this happens. Of course, you have to be a little bit careful when you're doing the integrals, but this is the basic idea. So it's because hyperballs are weird in high-dimensional geometry in some sense that the probability mass doesn't end up getting concentrated near near the origin, and so the probability mass all ends up being, most of the points are in this radius because that annulus at around the distance of root d just has a lot more points, and so that's where you sort of the balance of the probability density function getting smaller and smaller, and the number of points adds up. And so that's how we get this radius of a Gaussian, and how most points are concentrated, most of the probability mass is concentrated in this annulus. Any questions about that? Okay. So that was the Gaussian Annulus Theorem, and we're going to use it now to prove the something about random projections. So first we need to set up the problem. So random projection. So again, we're going to get a bunch of different points in R to the d, x1 through xn. These are all points in a d-dimensional Euclidean space. Then for b for some other point, so you're given a query point b in R to the d, we want to find the nearest neighbor. You find, let's write this, argmin sub I of x sub I minus b. Okay, so this is just the nearest neighbor problem, nearest neighbor. Anyone have any ideas? How would you find the nearest neighbor to a point in the high-dimensional space? Or just in any space? What's the naive approach? Yeah, exactly. That's a perfectly good naive approach, and often it ends up working. And many applications do this in practice. You just brute force it. If your data set isn't too big, you just look at every single point, see which one's the closest. So the naive approach is you brute force it, and you compare against each of your xi's, against each xi. And note that so you have O of n comparisons, because you're comparing against, well, n different things, which you can't really be helped in some sense. And another thing is, note that it takes O of d operations to compute the distance, to compute xi minus b for a given I. Because you have d dimensions, and so of course you have to compare each of those entries. And so you end up getting a total runtime of O of dn. Now, this isn't so bad when you're in low dimensions or if you don't have that many points, but if you're in a super high number of dimensions or you have a lot of points, well, this might be suboptimal. So can we do better if we're allowed to pre-process it? And of course, the answer to that is yes, because if you couldn't do better, then that would basically destroy the entire field of databases. But that's the question we're going to ask. And there are a bunch of different ways of answering this. So if you're from more of an algorithms computer science background, you might be like, oh, well, we can build some sort of tree, maybe build a Voronoi diagram or something like that. Do some sort of clever cluster.
Divide and conquer.
Yeah, so you can do some sort of divide and conquer. Maybe you do some sort of clever locality sensitive hashing. There are a bunch of different ways of solving it. We're going to present a way that involves making use of these properties of random Gaussians and this idea of random projections. So this is another approach. And so this is going to be theorem 2.10. It's going to be the random projection theorem. Random projection. And what are we going to do? We're going to consider a matrix. I'm going to call this matrix A, which is going to be filled with Gaussian random variables. We pick Gaussians because Gaussians are really nice to work with. As I'll mention later, you don't have to use Gaussians, but Gaussians make all the computations easier. So where each of our uij's is drawn from a normal distribution with mean 1 and variance, mean 0 and variance 1, and these are all iid. Okay. And ideally, we want k to be less than, much less than d. Because if k is bigger than d, well, you're projecting into a bigger space, and that doesn't help you at all. So what are we then going to do? We're going to let V be a point in Rd. Then there exists some c greater than 0, such that for epsilon in 0, 1, probability that, let me actually do this in a couple different colors just so it's clear where my bounds are. So the norm of AV minus this root k times the norm of V, take the absolute value of all of that, is going to be greater than or equal to epsilon times the square root of k times the norm of V. So the probability that the distance of your projected value, the probability that is far away from what you'd expect based on the original distance, is going to be less than or equal to 3e to the minus ck epsilon squared. Okay, so this A matrix is projecting down. So it's projecting from this high d-dimensional space into the smaller k-dimensional space. And what we want to say is we want to say something about the preserving norms. And that's basically what we're formalizing here. So, well, let's prove this. Proof. And we're going to make use of all these random Gaussians. So first, without loss of generality, we're going to assume that the norm of V is equal to 1. And we're going to say that we're going to write out the coordinates. V is equal to V1 through Vd. Okay, if it's not equal to 1, just scale everything. So the norm of V is equal to 1, and we can write out its coordinates. Well, we can just write out the matrix multiplication. This is something we guys did back in 222 or 223, whichever class you took. So what's AV? AV is just equal to U11 V1 plus dot 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 plus U1 D Vd all the way through UK1 V1 plus dot 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 plus UKD Vd. And I'm going to call each of these terms W1 through WD. So we're going to let Wi be equal to UI1 V1 plus dot 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 plus UID Vd random variables. There is a very cool result from probability, which I'm not going to prove, but you can prove it a number of different ways. Usually people use the characteristic function since things fall out pretty nicely from there. But we're just going to use this result with probability. So the sum of independent Gaussians is Gaussian. Okay, so it's some kind of Gaussian. We don't necessarily know its mean or its variance, so we do need to compute those. So let's compute its mean and variance. So since each of our Uij's are mean 0, variance 1, that means that the expectation of each of our Wi's. So you want to tell me this one? So yeah, linearity of expectation. This is just equal to 0. And of course, you can do something similar with the variances. So the variance of the Wi's is just equal to the sum over j equals 1 to d of vj squared times the variance of each of our individual things, ij. And what's this? Yeah, it's just 1. It's norm of v. We, without left generality, we assume that the norm was 1. And so that means that we are left with, plus we have wi, each of these are Gaussians with unit variance and mean 0. So we have W is a k-dimensional spherical Gaussian. And therefore, we can just apply the Gaussian Annulus Theorem by applying the Gaussian Annulus Theorem. We complete the proof. So what are we saying? We're saying that this random projection with high likelihood, roughly speaking, preserves the norm of a vector. And so if you recall what we did last time, well, if you can show that it preserves one norm with high probability, and this is exponentially high probability, you can set the constant up so you can say, oh, well, then it really ought to preserve n norms or n squared norms just by changing the values of, by changing the failure probabilities and the amount of leeway we're giving in terms of epsilon. So that brings us to the Johnson-Lindenstrauss theorem. Is there any questions so far? I've been going relatively quickly. Nope. Okay, great. So theorem Johnson-Lindenstrauss JL, which is for any epsilon greater than 0 and less than 1, and any integer n, we're going to let k be greater than or equal to 3 over c epsilon squared, with c from the Gaussian Annulus Theorem. So we're going to take that constant. Obviously, if you make your Gaussian Annulus Theorem tighter, then that translates here. Then, for any set of points, a set of n points in our original space, our d-dimensional space, the random projection which takes points from r to the d to r to the k by multiplying by this matrix, has the property that for all pairs of points, vi and j, with probability at least 1 minus 3 over 2n, we know that the distances are preserved. So I'm going to write that out, but basically all I'm saying here is that all the distances are preserved to within the factor of epsilon and root k. Sorry, it's a lot of writing. But basically all this is saying is that we're preserving all the pairwise distances with high probability. So does anyone want to say what method from probability, what bound from probability we're going to use to prove this? We used it multiple times in the last lecture. I have a bunch of events that I want to constrain. I am able to constrain the probability of a single event. And now I want to constrain the probability of a bunch of events of that type. Yep. Yeah, union bound. So we're going to just, the proof is application of a union bound. So apply union bound for every pair of points. For every pair of points after using random projection. So note that if k is greater than or equal to 3 log n over c epsilon squared, then we know that 3e to the minus ck epsilon squared is less than or equal to 3 over n cubed. So note that we chose the 3 very deliberately so that we'd have an n cubed in this in the denominator here. And how many pairs of points are there? So there are n choose 2 pairs of points, and n choose 2, well, I mean, we know what that is, but we can bound that by n squared over 2. N squared over 2 is a good enough bound. So pairs of points. And so what we're just going to bound is each of these distances. So the probability that any pair of points has large distortion. Distortion is the term that people often use for these sorts of embeddings. Basically, how far off the distances get messed up by doing this projection down to a lower dimension is less than 3 over 2n. And that completes the proof. So basically the key here is that because we multiplied our vectors by this random matrix of random Gaussians, we've suddenly turned all of our original points into random Gaussians in this lower dimensional space. And we know certain properties of these random Gaussians in lower dimensional space, one of which is this preservation of distances. And so it turns out that all you have to do is, if you multiply things randomly, things might work out, assuming that you set up the expectations correctly. So how does this help us in our original problem? Our original problem was we wanted to find this nearest neighbor, right? So let's think about the time complexity of being this random projection and searching in. It's obviously going to be lower in some ways because you're only searching over a lower k-dimensional space. So we're going to set k to be equal to O of 1 over epsilon squared log n. So if k here is less than d, we reduce the dimension. So how long does it, comparing points in Rk takes only O of k time instead of O of d, because their dimension is lower. So comparing, if I can spell, comparing all endpoints, O of dn goes to O of kn instead, which is equal to O of 1 over epsilon squared n log n. And so in some sense, this sort of makes sense, right? You ought to think that if you're going to do this comparison against all your points, it ought to be dependent on your points, not on the space itself. Or at least that's a sort of intuition we're trying to formalize. Like somehow the dimensionality of these, if you have a really high dimensional space, it doesn't really matter if you don't have that many points. And so if you don't have, like, if I give you 3 points in the high dimensional space, it doesn't really matter that they're in the high dimensional space. It's still enough. It doesn't cost you that much to compare against them. So let's see. And what we're going to do, of course, we now incur a pre-processing. Oh yeah, go ahead.
How much does it cost to do multiplication?
Yep, that's what I was about to get to. So we do now incur a pre-processing penalty because we have to multiply all the original points and we have to multiply each point that we're now querying. So we need to add that time to this. So projecting down from R to the D to R to the K, well, that takes O of KD time per point. Because of course we have a K by D matrix, and so you have to multiply by all the entries, and so it's going to take O of KD time to project each point. This is a little bit of an issue. So the overall query takes O of KD plus KN time, which is equal to O of 1 over epsilon squared log n times n plus d time. So unfortunately, we still end up with this. D term because, of course, you're still you have to project every point down, and you also get a pre-processing time, and you have pre-processing, which takes O of KDN time to build the database. So it still is a win, but it's not that much of a win. And the reason for this all is because A is a dense matrix. A is a dense matrix. Dense matrix with KD entries. Now let me ask you again, why is A a dense matrix? What did we do that made A a dense matrix? Oh, sorry. So a dense matrix is a matrix where most of the entries are non-zero. And this is our A matrix here, which we're using as a projection matrix. And so in order to project something down from a higher d-dimensional space down to k dimensions, you multiply it by this matrix, by this rectangular matrix. And you end up with a lower dimensional vector. But now the problem is, of course, that we filled it with these random Gaussians. And so what this means is that we actually have KD terms in here. The reason we did that is because it made all our proofs easier. But if you think about it, the sort of general gist of our proof doesn't really depend on Gaussians in some sense. What it depended on is being able to do these concentration inequalities and being able to say things like, oh, well, most things are concentrated near their expectation. And so because of that, one might wonder, well, can we use a different random variable that's maybe harder to prove stuff about, but gives us much further computational complexity? And this was the subject of a number of really brilliant papers back around 2010 or so. So the answer is yes, we can do a lot better. So what we did, not we, but So these are some papers by King, Nelson in 2010, or by Gupta, Kuhner, and Sarlis in 2010, and a number of others around the same time in conferences like Stock or Fox and Soda. So what they did is they proved that we don't need Gaussians. We don't need Gaussians, and can use things like sparse Bernoulli random variables instead. Sparse Bernoulli minus 1/2 matrices. So basically what we're doing instead is we're choosing a different random variable. So Gaussians have list distribution, right? But what if instead you just chose a random variable that had list distribution? Or even better, if you choose a random variable that has list distribution. So what are we doing here? So if you put a lot of you can think of it as taking a random variable that has probability mass of just 2 points, the two ends, maybe minus 1/2 or 1/2, depending on your scaling. And you put a lot of mass also on 0. And so if you put a lot of mass on 0, that means that a lot of your entries in your projection matrix will be 0. And it turns out that multiplying by a sparse matrix can be a lot faster than multiplying by a dense matrix, because you can just sort of ignore all the places where it's 0. And so you can think of this as you're just taking particular coordinates from your original high dimensional space and hoping that you're not getting rid of any important information and just like sparsifying it out that way. But assuming that you choose your random variable properly, and your data has, but assuming that you're choosing your random variable properly, you don't run into that problem, and you can actually prove that a very random variable that looks like lists will also get you the same sort of embedding properties, usually with a worse constant, but this is often computationally a lot cheaper. And that is like the proofs for those things are a lot more sophisticated and really beyond the scope of this class, but the papers are quite but the sort of flavor of what you're doing is the same. You're bounding these concentration inequalities, and from these bounds, you're able to show that all your points are still likely to be embedded with low distortion. And that basically is Johnson-Lindenstrauss. And so if you hear about things like Sparse JL, like that's using techniques like this. So, and if you're actually going to apply this in practice, using a dense Gaussian matrix is very expensive, because Gaussian random variables are also a lot more expensive than a 0, 1 random variable to generate. And so there are just multiple things about it that are more expensive. And so in practice, you don't tend to use these random Gaussians. Instead, you use these other sparser matrices, or matrices that are just basically use less bits of randomness in order to design. Okay, I have a couple more minutes. I'm going to talk a little bit about, do I have enough time to talk about this? Yeah, I have enough time to talk about this. I might end up not having time and finishing on tomorrow, but so I'm going to talk about a related topic. So we've sort of ended with this Gaussian with the Johnson-Lindenstrauss, and so we're just going to talk a little bit more about these spherical Gaussians, because those tend to show up in practice, because Gaussians show up all the time in real data. And so let's talk about a very simple Gaussian mixture model. So what we're going to do is we're going to assume our data comes from a mixture of two different Gaussians, and we're going to try to separate our data into the two original distributions. So let's say we're clustering a mixture of spherical Gaussians. And this is a simple Gaussian mixture model. And we're not going to do anything advanced here. There's an entire theory to Gaussian mixture models, which we might cover in class, or we might not. It's a bit too machine learning-y to fit in with all the rest of this class, but I might mention it a little bit. But so now the task here is we're going to partition a set of points into two subsets, or clusters as they're sometimes called. Clusters where each cluster consists of points drawn from a spherical Gaussian. And determine the parameters of the Gaussian. Okay, so basically our assumption, our model hypothesis is that our data comes from two different Gaussians. Like maybe the heights of men and women, you've mixed them all into some big batch of things, and you're trying to say, oh, well, is this point the height of a man or a height of a woman? And it might be hard to separate out because there's a lot of overlap between those two Gaussians. But that sort of idea, just in high dimensions with much higher dimensional feature spaces. We're going to guess that they're all spherical Gaussians to make life easier. So let's give a proposed naive solution. So proposed naive solution, which would never actually be used in practice, which is we're going to, but some of the steps are sometimes used. So the first step, we're going to just cluster using any clustering method, cluster our data by grouping nearby points. Think of this like k-means if you've seen that before, but like it doesn't really matter. We're just going to assume we have some way of lumping together the data points that are close to each other. And two, we're going to fit a Gaussian to each cluster. And it turns out this is easy because the best fit spherical Gaussian is just the one that has the empirical mean and variance of your data set. And so these are both really easy things to do. And sometimes it works and sometimes it doesn't. So for example, if this happens, actually, let me draw this better. If this happens, and those are your two starting distributions, this is really hard to cluster because they overlap a lot. Difficult to cluster when lots of overlap. But on the other hand, if the Gaussians are well separated, so obviously they will overlap because Gaussians don't actually go to zero. But if they're well separated, then let's say this has meaning mu1, this is meaning mu2, then this is easier when they're far apart. When far apart. So like if I measured a bunch of heights, some of the heights were of mice and some of the heights were of men. Well, it turns out that if you're measuring heights of mice and men, it's very easy to separate out because mice tend to be a lot shorter than men. So it's easier when you're far apart. For example, if you had that mu1 minus mu2, the distance between those was at least 6 times the maximum of your two standard deviations, and that implies there's less than 0.03 overlap. So now this is in one dimension, right? So in one dimension, you have to worry about them being far apart. But now what about in high dimensions? Well, in high dimensions, we know a couple of interesting facts about high dimensional Gaussians, right? One of which is that almost all the mass is concentrated in an annulus around the radius of the Gaussian. So in high dimensions, well, if we know that if 2 points are drawn from the same distribution, mu sigma, actually, did I mean sigma squared? I don't actually know what I meant. X and Y, sorry, I'm running a bit out of time, so I'm rushing. So if they're drawn from the same distribution, then we know that the distance between the 2 points is approximately equal to twice the radius. It's approximately twice the radius of the Gaussian because we know that almost all points are near the radius, right? And we also know that almost all points are orthogonal because we're in a high dimensional space. On the other hand, if they're drawn from two different distributions, let's say this is mu1, I'm going to keep their variances the same just to make life slightly easier. And let's say the distance between the two centers is equal to some value delta. Well, then we know that the distance between the 2 points is approximately equal to 2 times root delta plus or minus something that's O of 1 squared, sigma squared, plus delta squared. And again, this is because all directions are orthogonal. So you can basically just add together the distance of the distance as well as the distances they are from their center, so the radii. And so if the delta is sufficiently large, so what we need is, okay, it is now 4 o'clock. I'm not going to write this all down. I'll put it in the notes later. But basically, if your distances are far enough apart, well, then you can separate them out nicely because you have these tight bounds on the distance, the pairwise distances between points that are within the cluster or that are not within the cluster. So if 2 points are within the same distribution, then their distances will be very tightly bounded. If they're in different clusters, their distances will also be tightly bounded. And so you can just look at all the sets of pairwise distances, and for about all points in the same cluster, their pairwise distances will all be approximately the same, as opposed to when you're looking at 2 different clusters. There are more sophisticated methods where you use things like SPDs to project down to a lower dimension instead of and still preserve some of these properties. We will probably not make too much use of them, but I just thought you should be aware. So I think that ends class today. Thank you all very much, and I will see you tomorrow. Let's see. Any other questions in chat, Eiler? If not, then I will call it a day, and I will see you all tomorrow.